So we continue our discussion the psychometric processes. Now we go to the dehumidification of moist air by cooling. If moist air is cooled below its dew point, condensation of moisture will occur. So considering we have here this diagram. So, this is the refrigerant, and this is state 1. So at state 1 we have air, we have the mass of air, the temperature, the humidity ratio, and the enthalpy. So also we have state 2 here. This is our state 2. We have the mass of air, the temperature, the humidity ratio, and the enthalpy. So this is the, to draw its psychometric chart. So that one, the saturation curve. Okay, so this is our this is our point 1, and here this is point 2. Okay, so we have here T2, and we have this T1 here. Okay, so extend this line. This is our dew point. Okay, so dehumidify from this one. Okay, this are put an arrow here from point 1 to its dew point and to point 2. Okay, so draw a vertical line again. This is the temperature of your dew point 1. Okay, so at this point, point 2, we have we extend this line here. And extend this line our 2 prime, and so we have that. We have this T2 prime is equal to T2 and this is equal to temperature of your wet bulb. Another one. Okay, so in here we have the humidity ratio 1, and in the horizontal line this is our humidity ratio at 0.2, and this is our dry bulb temperature. Okay. Moist air is cooled below its initial dew point temperature. We assume that the air is uniformly and perfectly contacted, which is an idealized situation. Moisture will be separated at a variable temperature ranging from the initial dew point to the final saturation temperature. Let us assume that all of the condensed moisture is brought to the final temperature T2 before it drains from the system. The process may be interpreted in 2 ways. For the moist air system alone, the process proceeds at constant humidity ratio from 1 to D and down the saturation curve to 2. For the total system of air and condensed moisture, the process is one of constant humidity ratio from 0.1 to the fog condensation at 0.2 prime. Thus, the steady flow energy and material balance equation are, you can write the equation through material balance, or the steady flow energy. So we can write that mass MA 0.1 H1 is this is H1, MA2 H2 plus Q 1 to 2 plus M F HF 2. Going back to our figure, so in here we have here we have this MF liquid is coming out here, and this is HF 2. Okay, so back to our equation. I forgot, we have here the Q from 1 to 2. Since this is a refrigerant, so this is process of cooling or moist air. Okay, okay, so now we continue. So we have the mass H1 is equivalent to MA 2H2 plus Q 1 to 2. know that the mass 1 is equivalent to the mass of air at point 2, and we learned from our previous discussion that this mass M A1 and W1 is MA2 W2 plus MF. So thus the Q1 to 2, this is MA times H1 minus H2 minus MF HF 2. So Q1 to 2, this is equal to MA H1 minus H2 prime. Okay, so MF, you can write MF, this is MA times W1 minus W2. Okay, so going back to our figure again for the psychrometric chart. In here, this 2 prime, we have the one, we have this H2 prime here, and we have this H2. Okay, so go now to our example. Moist air enters a refrigeration coil at 80 degrees Fahrenheit dry bulb temperature and 50% relative humidity at the rate of 200 pound per minute. Barometric pressure is 14.696 psi or pound per square inch, and that is atmospheric. The air leaves saturated at 50 degrees Fahrenheit. Now calculate the tons of refrigeration required. So using those equations that we discussed a while ago, and by determining these properties of our psychrometric chart, so we have this one, the Q1 to 2, this is equal to this is 200 times this is 31 wait 200 times 31 31.2 minus 20.3 minus 0.0 0.1096 minus this is 0.00766 times 18.7 or 18.07. One. And this is equivalent to 2168 BTU per minute. This is in BTU. Per minute. Okay, so converting this to tons of refrigeration, we have the tons of refrigeration. The tons of refrigeration, TOR, we have 2168 divided by 200. So this answer is 10.8. Okay.